All right, what's up, everyone? My name is Michael Rossetti, and I'm here to talk to you about a research project I've been working on with my colleague, Tauhid Zaman, entitled OpenAI Text Embeddings for User Classification in Social Networks. Bots are automated social media accounts programmed to act in coordinated ways to manipulate online discussions by artificially inflating the popularity of certain posts. Twitter is full of bots. Or at least that's what we found in our previous research study, in which we collected a data set of tweets about the first impeachment of former President Donald Trump. In that previous study, we classified whether each user was a bot or not, using methods based on statistical physics. We then assessed the activity levels and persuasive influence of the bots. We found that although bots comprise less than 1% of all users, they're responsible for posting around 1/3 of all impeachment-related content. And we found around 1/3 of users follow at least one bot. To combat the influence of bots, it's important to be able to detect them. As adversaries use new methods to program the bots, our detection methods must evolve as well. We'll return to talking about new methods in a few minutes, but in terms of our previous research, besides bot classification, we performed a number of additional classification tasks as well, including classifying political opinion, language toxicity, and news quality. To classify political opinions, we trained our own natural language processing model based on a BERT transformer. This model requires labeled data and took a while to train. To classify language toxicity, we used a pre-trained model called Detoxify, which has demonstrated excellent performance in Kaggle competitions related to detecting toxic and inflammatory language. Finally, to assess the quality of news being shared by each user, we looked at which users shared links to news articles, then cross-checked the links against a third-party list of news quality scores for each media outlet, produced by a study from Pennycook and Rand. As you can see, for each of these 4 classification tasks, we use different methods, and each method serves only a single function. But could one single method be used instead? And are there any new technologies we could explore for this purpose? ChatGPT by OpenAI is a groundbreaking new technology based on large language models. Many scholars believe this technology can make bots harder to detect. For example, if adversaries use the technology to generate customized content for bots to post. However, can this new tool be used to find the bots? This is what we said to find out. Most of us have used ChatGPT through the web interface by exchanging text messages with it. However, we can also interface with large language models programmatically using the OpenAI API. Through the API, we can interface with a text embedding model, providing it with some text and receiving the corresponding embeddings, which are numeric representations of the text. Through the text embeddings, we can gain insight into how a large language model represents language concepts. The embeddings encode certain language patterns and relationship in high-dimensional space. Embeddings that are numerically similar are also semantically similar. For example, if we reduce the number of dimensions to plot the embeddings on a graph, we can see the word cat occupies a similar space as the word kitten, denoting these words have a similar meaning. Embeddings also convey relationships between words. Here we see the relationship between the word man and the word king is similar to the relationship between the word woman and the word queen. So, these embeddings are powerful representations of text, but how powerful are they? And can we use them to train machine learning models to find the bots? This is our primary research goal. In terms of our research plan, first, we'll take a random sample of users from our impeachment dataset. Then we'll prepare their tweet timelines as text. Then we'll obtain text embeddings from the OpenAI API. And finally, we'll use the embeddings to perform classification. We pulled a random sample of around 7,500 users from our first impeachment dataset. For each user, we have labels from our previous research about that user's bot status, political opinion, language toxicity score, and news quality score. For each user, we concatenate all their tweets into a single string representing their timeline. We could have obtained embeddings for each tweet separately and averaged them for each user at the end. However, obtaining embeddings for each user is cheaper and simpler. And we'll see later how this approach has the potential to not only encode the language content, but volume as well, since some users tweet more than others. We then take these user timeline texts and exchange them for text embeddings from the OpenAI API, where each set of embeddings represents a given user's tweet history. Finally, we use these text embeddings to classify a number of different targets. When performing classification, we used a handful of different models, including logistic regression, random forest, and XGBoost for benchmarking and comparison purposes. So how did we do? Here we see the classification results. It turns out we are able to use the embeddings to classify each of the targets with high success. We see the results depend more on which target we're classifying than which model we're using. The different models perform more or less the same for each target. One potential reason why news quality classification is less successful is that only a small number of users share links, leading to a smaller training set. Users who don't share links don't have news quality scores and are excluded from model training. So we were able to succeed in our research goals, but let's dig a little deeper to better understand how the text embeddings represent information that can be used to perform these different classification tasks. Let's focus on the qualities inherent in the text embeddings themselves. These embeddings come from OpenAI in 1,536 dimensions or columns. We can use an unsupervised learning technique called dimensionality reduction to compress or project all of this data into a smaller number of dimensions or columns. When we do this, we choose the number of columns we want to wind up with. This is a form of lossy compression, so a larger number of dimensions will more fully explain variations in the data, while a smaller number of dimensions will explain less of the data. Although it won't fully explain the data, choosing 2 dimensions allows us to chart these projections on an XY plane, which our human brains can more easily interpret. When performing dimensionality reduction, we use 3 different methods for benchmarking and comparison purposes. These methods include PCA, TSNE, and UMAP. Each of these methods projects the embeddings differently. First, let's take a look at PCA. Here we see the PCA projected embeddings in 2-dimensional space, where each point represents a user. On the x-axis, we see values for component 1, which represents the first dimension. And on the y-axis, we see values for component 2, which represents the second dimension. Since this is an unsupervised approach, it's up to us to interpret what these components mean. When we color the points on bot status, we see a concentration of bots in purple on the left side of the graph, where component 1 values are less than around -6, and a concentration of users on the right side, where component 1 values are greater than around -6. So if we interpret component 1 as representing bot status, we can draw a line to separate the data. As such, we can expect a simple linear classifier to be able to distinguish between bots and humans. But what qualities in the underlying data are helping PCA do its job? When we examine the volume of content posted by users, we see bots post a much larger volume of content than humans do on average. So our original decision to encode the entire user timeline with varying lengths, rather than encode each tweet individually, is likely enabling the text embeddings to represent information related to volume of content. All right, so we looked at bot status and talked about volume of content, but let's stay on these PCA projections for a moment and examine the content itself. When we color the points based on political opinion, we see pro-Trump users are represented towards the top of the graph, where component 2 values are positive, and anti-Trump users are represented towards the bottom of the graph, where component 2 values are negative. So it appears PCA may be able to explain both bot status and political opinion separately in just 2 dimensions. But now let's explore alternative dimensionality reduction methods, which may project the same data in different ways. Here we see the users as projected by TSNE and colored on political opinion as well as bot status. As you can see, as compared to the PCA projections, these TSNE projections make it easier to linearly separate the users based on political opinion. And the same goes for projections from our final dimensionality reduction method, UMAP. However, in each of these cases, we see some red dots mixed in among the blue cloud, indicating it may be harder to separate pro-Trump users than anti-Trump users. But why might this be the case? When we dig deeper into the formal classification results, we see anti-Trump users are classified with a higher degree of accuracy than pro-Trump users. When we examine the kind of language being used by pro-Trump users who have been misclassified, we see some anecdotal evidence to explain this. For example, some have used phrases like impeach Trump or remove Trump, which, when taken out of context, are similar to the impeach and remove rallying cry used by anti-Trump users. So we've gained some intuition about bot status and political opinion, but finally, let's look at news quality. As exemplified here with the UMAP projections, when we color the users on news quality, we see 2 distinct concentrations of users. The concentration of users in the top left share low quality news, and while the concentrations of users in the bottom right mostly share high quality news, there are a number of low quality users mixed in. This may help explain the relatively lower classification performance for news quality, but we also remember that when this data is represented in higher dimensions, it may be more able to linearly separate these 2 groups. So, in conclusion, text embeddings from large language models, such as those obtained from OpenAI, are effective and powerful representations of language. They can be used for a wide range of user classification tasks in social networks, and they can facilitate the usage of simple models for high accuracy classification. Thank you. Thanks for your attention. Have a nice day. Encore? Okay, sounds good. So we were able to use a single method to perform all of these classification tasks, but what about a single model to predict the simultaneous joint outcomes among multiple classes? For example, trying to classify bot status and political opinion at once, or all of these labels at once. Here are the results. We see that when we perform multi-class classification, the results are almost good as the binary classification equivalents. But when we start adding more and more classes, the results don't do as well. And this is mostly because when we increase the number of classes, the size or the number of users in each class decreases. And so moving forward, we might consider using a larger sample than 7,500 users to make sure there's enough users in each of these classes to see if we can improve the classification accuracy a little more. But anyway, it seems like it does all right. So anyway, Encore, nice. Peace out. Have a nice day. Thanks for your attention.